And with linear, quadratic, and exponential models, the big thing is how they change. And we have looked at these things before, and so hopefully this will be just a little quick reminder for you that when we're looking at linear functions, okay, it's either going up or going down by the same amount each time. If it's a quadratic, then it'll either go up and then come back down like the height of a volleyball, or it'll go down and come back up. Right? So either it makes a U shape or a upside down one. And exponential, we know that either that's growing or decaying, and we know what they look like. So we're going to look at the different types of functions and be able to tell whether a set of data is going to match one function or the other. And then we're going to probably add to that a little bit of finding out what that function is according to the information. So we're going to be doing a little bit of graphing, and we're going to use a graph here first of all to figure out which is the best model. And hopefully some of these you'll be able to figure them out right away by looking at the graph, and then we'll talk about how you can do it by figuring out what's happening with the data. So if I put a graph in here, not a table, put a graph. Now, in this graph I'm going to do here, I've got these numbers 0, 1, 2, 3, and 4, and 24, 96, 384, 1,536, and 6,144. So should I make a Cartesian graph or just a quadrant graph for this? Okay, because these are all just positive numbers, right? Okay. So we can go with a quadrant graph. Okay. Now the next thing I need to do is I need to be able to do my axes for my quadrant graph. So my x-axis should be what? Okay, start at 0, goes by 1s, right? We could go up to 10, or, even if we went to about 7 or 8. We want to go a little bit more than 4 anyways. Now, what about our y-axis then? I've got to be able to see all the way up to 6,144, right? Okay. So I need my y max here then, where I'm going to end, needs to be at least that, right? So I'm going to have to go up to probably like 6,500. Hey, look at that. Okay. And so what should my steps be by then if I'm going to go all the way up to 6,500? Okay, 500 is just not bad because that would put me at 13 of them then. We could live with that. Okay, all right, much better. Okay. Now I could get rid of the horizontal and vertical lines, so it looks like that, but actually what I'm doing is going to help me. So, all right, so we'll finish it. Okay. And it's up here. Yeah. All right, so we'll go ahead and then plot these points. 0, 24. Where's 0, 24 at? And it's like right here, right? Okay, and 196, well, that's not going to be a whole lot higher up, is it? Okay. 2 and 384, okay. It's a little bit past halfway. Oh, this one helps. 3 and 1,536. That's about right on the line there, a little above it. And 4 and 6,100. All right, so if I drew a line here through these points then, to represent them, what would we say that is? Okay, that would definitely be exponential. A nice exponential function. Now, with that nice exponential function, could we find a rule for that? Now remember, for exponential functions, our general formula is that y equals a times b raised to the power of x. Do we know the value of a in this case? Okay, Brandon, what's the value of a? 24. That's when we cross the x-axis, or the y-axis, excuse me. So we have 24 as our value for a. Can we find the value of b then? All right, so Mr. Farmer, how do I find the value of b? All right, he doesn't know. Montana, do you know? All right, Teresa? Does anybody? Anybody know how? All right, we have a couple people. All right, Josh?
You take like 96 divided by 24, 384 divided by 96.
Okay, so we take our bacteria values here, and we're going to divide them. All right, so let's see. So on our home screen, we'll check out a couple of them. Maybe. I don't want that. Graph and clear. That works for you? Well, it's not working for me. All right. I guess it's frozen. Yeah, I understand. Sure. Interesting. All right. Nope, it's all messed up then. All right, so you guys do it for me. So I'm going to divide all these. So 6144 divided by 1536. 1536 divided by 384. 384 divided by 96. 96 divided by 24. And each of them I get, 4. So that's my value of b. So this is going to be y equals 24 times 4 raised to the power of x. That would be my function rule for that problem. So when you figure out what it is, you should be able to write a rule that matches it according to the given information. Let's try this next one here then. Here we have reams of paper. Now, as reams of paper is going to be a little bit tougher for us, so we'll pull our wizard out here again. Okay. All right, so should we use a Cartesian or a quadrant for this one? Okay, quadrant. All right. And let's see, our end values for our x needs to be, at least for our x, number of boxes needs to be at least 50, right? So we better go past that. So let's go to, we don't want to go to 100. That's a little more than we need to, but maybe 60. Should we just go by ones or should we go by, all right, by fives? Okay, we can go by fives. All right. How about our ending value for our reams of paper then, which is the y values? All right, so we need to go above that. So let's go to 600 there. And how about our step? I know. Let's go by 50, so 600. Or what do they say? 600, yep, okay, all right. And what's that? Oops. All right, so we've got reams of paper here. So we've got the point 110 10. That's going to be pretty low then. That's about right here. 5 and 50. 20 and 200. And 50 and 500. Okay. All right, so our graph is going to look like this then. Oh, that looks like a nice straight line, doesn't it? Okay, so that would be linear. All right. And then we want to, if we can, find an equation for that. So what does a linear function look like? What's the general formula for a linear function? Okay, but what's the y equals what? All right. Josh, you remember?
mx plus b.
Okay, so y equals mx plus b. All right. So in this case, b is our y-intercept, where it crosses the y-axis, and m is our slope. All right, so for a linear, we got y equals mx plus b. B is where it crosses the y-axis, and m is the slope. So we're going to go ahead and find the slope. How do I find slope? Because I don't have a 0 up there for my y-intercept, but we can figure that out in a minute once we know what the slope is. How do I figure the slope? Okay. Remember, slope is the rise over run. That's right. Slope is the change in y over the change in x. All right, so we take any two y values and subtract them, and the corresponding x values, and we subtract them. Okay. So does it matter which two I pick? No, it doesn't. But you could see this one. I can see this one right away. I don't know if you can or not, but I can see this one right away. Because how do the y values compare to the x values? Okay, they're 10 times bigger, right? Okay, so I want you to think about this for a second. All right. So if they're 10 times bigger, what's the slope then? Okay, so let's pick any two. Let's go. I'm going to use the easy ones. 50 minus 10 over 5 minus 1. So 50 minus 10 is 40, and 5 minus 1 is, okay, and 40 divided by 4 is, okay, so the slope is 10. Now, let's think about this, okay? You guys are all very smart, okay? If I have 0 boxes, how many reams of paper am I going to have? 0, okay? So what's the y-intercept in this case? 0. So this would just be y equals 10x. So every box, so when we get a box of paper in the office, there are 10 reams of paper in each of those boxes. Okay? So, which is actually the case as it is here. So we kind of went a little bit ahead of ourselves, but we're good. Okay. All right. So graphing them, figuring it out, and we could even write the function. Okay. All right. Now, what if it's not quite as clear what it is? Well, most of them are going to be very clear of whether it's linear and exponential. Those two obviously were, right? Okay. Right. But sometimes quadratic and exponential actually look kind of similar when you're looking at just the points. Because I actually could have looked at this set of points here, and if all I cared about was the set of points instead of the line, I might not have been so sure about whether this was quadratic or exponential. Right? But because there's this huge gap here, really made me sure it was exponential. Okay, and then when I did my work with the numbers, I knew for sure it was. But that's not always the case. But there is an easy way too with most quadratics. Okay, so look at these numbers here. We have 0, 1, 2, 3, and 4, and then we have heights of a golf ball, 4, 68, 100, 168. So the easiest way to tell whether you have a quadratic would be what? Mr. Shink? What would be the easiest way to tell if I have a quadratic? Okay, the second difference. That would be great, but that's not the easiest way. Okay, that's one way. You read this, didn't you? Good reading. Good job. Okay, all right. You can. All right. Now, look at these three. Linear, quadratic, exponential. Okay. Now, linear, we know one of two things is going to happen, okay? Either the numbers are always going to be getting bigger or always getting smaller, correct? Okay, they can't be anything different than that. Always bigger or always smaller for linear, okay? And then the change between each y value is always going to be the same, okay? All right, the quadratic, all right? With a quadratic, the graph either goes up and then comes back down like this one does, which what happens with the y values then? They get bigger and then they get smaller, okay? Or this graph could look, or it could look like this, which means that my y values are going to get smaller and then bigger, okay? All right. And then exponential, all right? Either we have growth, which means they're continually getting bigger, or we have decay where they're continually getting smaller, correct? Okay. All right. So, always, okay, before you do any calculations, look at what's happening with the numbers. Because sometimes it's just going to give it away to you. All right. Mr. Beebe.
It does this.
Okay. All right. Yep. My heights of my golf ball go up, and then they come back down. So this is a quadratic. Yes, sir.
I always call them like it goes up and then down. I always call them sashes.
Right.
So that's,
Yep.
that's how it makes it easy.
Okay. Now, let's check this out for sure using differences, just to verify you know what to do here. All right. So I'm always looking to make sure my x or my independent variables change by a constant. Okay. And these all change by 1, right? 4 minus 3 is 1. 3 minus 2 is 1. 2 minus 1 is 1, and so on. Okay. Now, when we're talking about using the differences like we mentioned over here, okay, the differences mean I'm going to take the next number and subtract the previous. Okay. So what's 68 minus 4? 64. So this first difference here, my first number is 64. Okay. 100 minus 68? 32. 100 minus 100? 0. Good job. All right. And 68 minus 100? Okay. Negative 32. All right. So we're good there. All right. Now, are those the same? If they were the same, what would it mean? Okay, that it's linear. Okay. First differences are the same, it's linear. All right, so they're not the same, so I'm going to subtract with these numbers. So now I'm going to put these together like this and subtract. Okay, and I'm going to work from the bottom. Okay, what's negative 32 minus 0? Okay, negative 32. What's 0 minus 32? Okay, negative 32, right? Okay, the sign matters. Okay. And 32 minus 64? Okay, all right. So since the second differences are the same, I have verified for sure that this is a quadratic function. Okay. So look for patterns. If we find the pattern, bingo, we got it right away. If we don't see it, then for linear and quadratic, we'll have to do first difference or second difference. If I'm not sure I need to do exponential, then we've learned how to do that. This chapter was talking about doing common ratios or find the constant ratio. All right? So let's look at this other set of numbers. Now, another thing is, sometimes look at what the problem is and think about it. Okay. So here we have, what does money CD mean?
Like how much the CD cost, like the amount.
All right, what's CD stand for? Do you know? It's a CD, one of those little round things about 4 or 5 inches in. No, I don't think that's what it's talking about. Okay, that's definitely not what we're talking about with a CD here. Okay, David. What? That would be one of those things you put in a computer. Okay. But I know what you're thinking about. Okay. All right, Josh. Okay, it's called a certificate of deposit. That's money you put in the bank, basically. Okay. All right, Josh is our answer man today. He's doing a good job. All right. Okay, so it's a certificate of deposit when we're talking about money. You can buy CDs, and your grandparents may have bought one for you when you were born, or given them to you for your birthday, where it's a certain amount of money that basically it's in the bank calculating interest for you. Okay, and so when I see a money in CD and it starts talking about that relates to interest. Well, what kind of a problem is interest? Well, the interest isn't very good. The interest rate isn't. But if I'm talking about a problem that has interest, what kind of a problem is that, David? That's, yeah, exponential growth. That tells me right away that this is exponential growth, and I can check it out then by finding the constant ratio. Okay? So certain things should tell you something right away. The fact that I'm talking about money, okay, usually they're talking about the growth or the, unfortunately, the decay of money, okay? So we're going to check out the constant ratios. So in this case, I check these out. All right, they're all ones. Great, okay? And now I'm going to divide. So I'm going to take 1,601.04 divided by 1,368.57. Okay? And I'm going to do that with each one of them, each pair. And I want to make sure that they're all either the same or they're so close that there's no question about it. Okay. And hopefully, when you do this, you get the same number each time. All right, which should be, if I divide by 1,000, how many places do I move my decimal? How many zeros are in 1,000? 3. So if I divide by 1,000, I should move my decimal 3 places. So if I divide this by 1,000, then I get this number here, 1.169, right? 86. All right, that's the actual number I'm going to get. Okay. Do I get that same number with these other two? Do I divide those other two? I don't know, my calculator's not working. You guys got the working calculators. You have to help me out. Okay. And they may not be exact, but it should be pretty close. I mean, if at least 3 or 4 decimal places are the same, then it's the same. All right, we're not going to argue with that because there is always rounding errors that do occur. Okay, so are these about the same? All right, at least the 3 digits. Okay, so our constant ratio produced the same thing, so this would be exponential. All right, we found that by doing the constant ratio, but think about the problem. What is the situation? Okay, sometimes it's a giveaway for us. All right. Okay, so we already talked about this. Took a real quick talk about this, but here's the general forms of those functions. And we spent time with at least linear and exponential already, which you're very familiar with because we've been working with them. Okay? And then we have the quadratic one, which you have worked with. Okay? But the quadratic one becomes a little bit more difficult at times, but only it's more difficult if you have the bx plus c. And most of the ones you're going to be dealing with are just going to have ax squared. So you just need to look at what's being squared. Okay? All right, so use a table to describe how the number of people changes. Then write a function that models the data. Use your function to predict the number of people who received the email after 1 week. Okay. Now, in my mind, I have an idea of what it might be here. Okay. So here we've got the time. In 0 days, 8 people have the email. Okay, so we're starting with 8 people. Right. Then after 1 day, we now have 56, 2, 392, and 3, 2,744. So what's happening to the number of people who receive the email each day? Is it getting smaller, getting bigger? Is it changing at the same rate or what? Okay, right, so you got to think about that. Okay, so in this case, those numbers are all getting bigger, aren't they? Okay, now, is the amount from 8 to 56 and 56 to 392, is that the same? No. Okay, so that means it can't be linear. Okay, we've just eliminated linear. All right, good. All right, we only got 2 left. Okay, all right. Now, so that means quadratic or exponential. Which is easier to check right away, quadratic or exponential? No, it's not. Exponential is easier because with quadratic you have to do differences twice. With exponential you just have to divide. Okay? So exponential is actually easier to check because all you have to do is divide. So what's 56 divided by 8? I hope it's only 7. Okay? All right. 56 divided by 8 is 7, right? That calculator says 56 divided by 8 is 7.375? That's a crazy calculator. Oh. All right, what's 392 divided by 56? 7, okay, so we have a constant ratio of 7, so this is exponential. All right. So that means we're using y equals a times b to the power of x, because it's exponential. A is my starting value. How many are we starting with? 8, right? At day 0, there's 8 people. Okay, and what happens to get to the next day and the next day and the next day? What are we doing? Okay, we're multiplying by 7. So we get y equals 8 times 7 raised to the power of x. And how many days are in a week?
7.
Okay, so 7 to the 7th power then would be how many people have it after a week. Or I could just multiply this number by 7 and keep going 4 more times. And that's a big number. 6, 5, 8.
3, 4.
So for after 1 week, 6.5 million people plus have that email. All right. All right. That gets about the state of Michigan. We're all good there.